Scientists have issued a stern warning. The first generation of Martian settlers may never return to Earth. The red planet, orbiting 55 million kilometers away, appears to be a promising second home for humanity. However, the harsh reality often glossed over is simple. While the transit to Mars takes only 7 months, a safe return journey is a nearly impossible feat. With average temperatures plummeting to minus 63 degrees Celsius, an atmosphere 100 times thinner than Earth's, and unshielded exposure to lethal cosmic radiation, every factor suggests that a mission to Mars is effectively a one-way trip. Why, then, are nations competing to colonize this hostile world? What underlying imperative drives this interplanetary race? The answer is fundamentally simple. Within the entirety of our solar system, Mars represents the only viable option for expansion. One might logically ask, is the Moon not a more accessible destination? The geological reality is prohibitive. The Moon completely lacks a protective atmosphere. Daytime surface temperatures soar to 127 degrees Celsius, while nightfall brings a plunge to minus 183 degrees. Such extreme thermal cycling would eradicate biological life within hours. As for our other neighbor, Venus, surface temperatures reach a lead-melting 463 degrees Celsius. The atmospheric pressure is 92 times greater than that of Earth, equivalent to the crushing pressure found 900 meters beneath the ocean. The human body would be instantly imploded by these forces. Only Mars, despite its desolate and barren appearance, offers a genuine probability for long-term survival. According to the latest data gathered by NASA, Mars shares 3 remarkably Earth-like characteristics. First, a Martian day, scientifically termed a sol, lasts approximately 24.6 hours. This is merely 36 minutes longer than a standard day on Earth. This allows the human circadian rhythm to function without major adjustment. Second, Mars has an axial tilt of 25.19 degrees. Compared to Earth's tilt of 23.5 degrees, the planetary alignment is nearly identical. Consequently, Mars experiences a familiar cycle of 4 seasons, though a single Martian year extends for 687 Earth days. The third and most critical factor is that Mars is situated within the solar system's habitable zone. Near the planetary equator, daytime temperatures can reach a mild 20 degrees Celsius, a condition theoretically survivable for humans. However, planetary geology reveals a disturbing history. Mars was once a twin to our own planet. 3.7 billion years ago, it possessed vast oceans, a temperate climate, and potentially harbored the conditions for microbial life. Why did this thriving world devolve into its current barren state? The scientific explanation is sobering. The Martian global magnetic field collapsed approximately 3 billion years ago. With this protective shield gone, solar winds acted like an abrasive torrent, steadily stripping away the planet's atmosphere. This process ultimately transformed a dynamic world into the lifeless, desiccated desert we observe today. Disturbingly, Earth's own magnetic field is currently showing signs of weakening. Should it eventually fail, humanity would face an extinction event similar to that of Mars. Therefore, the colonization of Mars is not merely an ambitious pursuit. It is a race against time for the survival of our species. So, what specific lethal challenges await us on the Martian surface? The primary logistical hurdle is water availability. In August 2024, NASA's InSight lander provided revolutionary seismic data. At depths of 10 to 20 kilometers beneath the crust lies a reservoir of liquid water vast enough to cover the entire planet. This global ocean could be up to 1.6 kilometers deep. This discovery has galvanized the scientific community, as the presence of liquid water implies the potential for sustaining life. However, a significant engineering challenge remains. With these reserves located kilometers underground, extraction requires technology far beyond our current capabilities. Proposed methods involve deep drilling combined with thermal injection to melt the subsurface matrix and pump the water to the surface. While the concept sounds straightforward, the operational difficulty rivals the most extreme deep-sea mining on Earth. Furthermore, Mars lacks any existing industrial infrastructure, meaning every system must be built from the ground up. The second existential threat is the lack of breathable air. On Earth, the atmosphere contains approximately 21% oxygen. In contrast, the Martian atmosphere contains a mere 0.13% oxygen, with the remaining mass composed primarily of carbon dioxide. Fortunately, a breakthrough occurred in April 2021. The MOXIE instrument aboard the Perseverance rover successfully demonstrated in situ oxygen production on Mars. It generated 12 grams of oxygen per hour, achieving a purity level of 98%. The operating principle is scientifically elegant. It heats atmospheric carbon dioxide to 800 degrees Celsius and uses solid oxide electrolysis to isolate the oxygen atoms. The entire process is powered by solar arrays. It sounds promising, doesn't it? However, there is a critical, potentially lethal limitation. 12 grams of oxygen is only enough to sustain a single person for approximately 17 minutes. To support a base with a crew of 12, you would need at least 100 of these units operating continuously. The third major obstacle is thermal regulation. While daytime temperatures at the Martian equator can reach 20 degrees Celsius, the planetary average hovers around minus 60 degrees. Nighttime temperatures plummet to extreme lows. The scientific consensus proposes constructing subterranean habitats buried at least 50 meters deep. This utilizes the thermal insulation properties of the Martian regolith, supplemented by nuclear power systems for heating. NASA is currently testing a prototype inflatable habitat. Constructed with advanced composite materials, the outer shell is designed to withstand temperatures dropping to minus 100 degrees and solar irradiance of 600 watts per square meter. Speaking of radiation, this is the most insidious threat on Mars. Lacking a global magnetic field for protection, the surface is exposed to solar radiation levels far exceeding those on Earth. Long-term exposure causes irreversible DNA damage, increasing the risk of cancer by 30% and potentially shortening life expectancy by 15 to 20 years. Even more alarming are solar flares, which release high-energy particles traveling near the speed of light in a matter of minutes. This leaves astronauts with a dangerously short reaction window. Without immediate access to a shielded shelter, the biological consequences would be catastrophic. Yet even these are not the most lethal factors. The challenge that truly perplexes scientists is the phenomenon of global dust storms. In 2018, a massive planetary storm swept across Mars, covering an area of 25 million square kilometers. This storm engulfed the rover that had been operating on Mars for 15 years. Its final transmission to Earth was poignant. "It's getting dark, and my battery is low." It was never heard from again. Similarly, China's Zhurong rover entered hibernation mode in 2022 due to dust accumulation and has yet to reactivate. Why are Martian dust storms so formidable? The fundamental cause lies in the extremely thin atmosphere. On Earth, the dense atmosphere acts as a thermal buffer, regulating temperature. Mars lacks this mechanism. Standing on the Martian surface during the day, the temperature at your feet might be 22 degrees Celsius, while at head height, it drops to sub-freezing levels. This steep thermal gradient generates ferocious winds exceeding 300 kilometers per hour, lofting dust high into the atmosphere. Because Mars's gravity is only 38% of Earth's, these particulates take months to settle, remaining suspended in the atmosphere and completely blocking out sunlight. Imagine the scenario. You have just established a base and planted your first crops when a massive dust storm strikes, lasting for months. Once the solar arrays are buried under a thick layer of dust, the base will lose power within 72 hours. As the oxygen supply fails, the crew will suffocate within their sealed habitat. How then does humanity propose to overcome these lethal challenges? Are there viable solutions? Regarding sustenance, scientists advocate for controlled environment agriculture. Essentially, this involves cultivating crops within sealed greenhouses. These systems use LED arrays to simulate sunlight, while strictly regulating temperature, humidity, and carbon dioxide concentration. Crops are grown in Martian soil, including potatoes, lettuce, and wheat. This technology has already been successfully tested on the International Space Station and in Antarctica. Plant growth rates can even exceed those on Earth. The low-gravity environment of Mars allows plants to grow significantly taller. However, there is a hidden danger. Martian soil contains high concentrations of perchlorates, a chemical substance highly toxic to humans. The soil must undergo rigorous decontamination to prevent chronic poisoning from the harvested crops. As for energy, while solar power is a primary option, the threat of dust storms makes it vulnerable. Consequently, scientists favor nuclear power systems. NASA is developing a compact nuclear reactor known as Kilopower. Weighing only 1.5 tons, it can provide 10 kilowatts of continuous power, sufficient to sustain the operations of a small outpost. The problem is how to safely transport such massive payloads to Mars, and how to assemble and maintain them on the surface, present formidable engineering challenges. At this juncture, one might ask, given these overwhelming obstacles, why does Elon Musk persist with the goal of sending humans to Mars by 2027? The answer is starkly pragmatic. This is a geopolitical space race between nations. In September 2024, the China Aerospace Science and Technology Corporation announced that it plans to execute its first manned Mars mission in 2033. The strategy involves launching 6 spacecraft in a single wave to establish a comprehensive Martian base. The United States, Russia, India, and the UAE all have entered this unprecedented strategic contest, for whoever establishes the first colony on Mars will command authority over future extraterrestrial resources. Yet, this raises a profound philosophical question. In our bid to escape Earth, humanity spends trillions of dollars attempting to terraform Mars, while hesitating to invest comparable resources to save our only home. 800 million people on Earth suffer from hunger, and billions lack access to clean drinking water. Have we fundamentally misaligned our priorities? Martian colonization may symbolize humanity's courage to explore the unknown, but we must never forget, Earth remains the most beautiful, most precious, and most habitable blue planet in the cosmos.